The National Electrical Code, specifically Section 210.19a, addresses the requirement to limit the load on a breaker to no more than 80% of its rating. This provision is in addition to the continuous load calculation of 125%. To understand this, firstly, it's important to define what a continuous load is. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. The NEC requires that branch circuits supplying continuous loads be rated for 125% of the continuous load, meaning the overcurrent device and conductors must be sized accordingly. Now, the 80% rule is closely related but somewhat distinct. It is another safety measure designed to prevent overheating and nuisance tripping of circuit breakers. The 80% rule essentially means that the total load connected to a breaker should not exceed 80% of the breaker's ampacity. For example, a 20 amp breaker should not be loaded to more than 16 amps. This is because circuit breakers are designed to carry their rated current continuously, but operating them at or near their maximum rating for extended periods can lead to overheating. Overheating can degrade the breaker's performance over time, potentially causing it to trip prematurely or even fail. The 80% rule provides a margin of safety to prevent this from happening. Now, to clarify the interaction between the 125% continuous load rule and the 80% rule, one can look at them as complementary requirements. The 125% rule applies when calculating the minimum ampacity of the branch circuit conductors and overcurrent protection device for continuous loads. The 80% rule places a limit on the maximum load that can be connected to a breaker, regardless of whether the load is continuous or non-continuous. Here is an example to illustrate the application of both rules. Suppose one has a continuous load of 10 amps and a non-continuous load of 5 amps connected to a circuit. Firstly, calculate the required ampacity for the continuous load, which is 10 amps times 1.25, which equals 12.5 amps. Secondly, add the non-continuous load to the result. 12.5 amps plus 5 amps equals 17.5 amps. This means that the branch circuit conductors and overcurrent protection device must be rated for at least 17.5 amps. Because standard breaker sizes are typically 15 amps, 20 amps, 25 amps, and so on, one would need to select the next higher standard size, which is 20 amps. Thirdly, check to make sure that the total load does not exceed 80% of the breaker's rating. The 20 amp breaker should not be loaded to more than 16 amps. 20 amps times 0.8 equals 16 amps. In this case, the total load is 10 amps plus 5 amps, which equals 15 amps, which is less than 16 amps, so the 20 amp breaker is acceptable. Another example would be if one has a continuous load of 12 amps and a non-continuous load of 4 amps connected to a circuit. Firstly, calculate the required ampacity for the continuous load, which is 12 amps times 1.25, which equals 15 amps. Secondly, add the non-continuous load to the result. 15 amps plus 4 amps equals 19 amps. This means that the branch circuit conductors and overcurrent protection device must be rated for at least 19 amps. Because standard breaker sizes are typically 15 amps, 20 amps, 25 amps, and so on, one would need to select the next higher standard size, which is 20 amps. Thirdly, check to make sure that the total load does not exceed 80% of the breaker's rating. The 20 amp breaker should not be loaded to more than 16 amps. 20 amps times 0.8 equals 16 amps. In this case, the total load is 12 amps plus 4 amps equals 16 amps, which is equal to 16 amps, so the 20 amp breaker is acceptable, but it's at the maximum load allowed. One should also consider voltage drop in the circuit. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% overall for feeders and branch circuits combined. Voltage drop can be calculated using a formula that takes into account the conductor length, current, and conductor impedance. Using larger conductors can reduce voltage drop, but this also increases the cost of the installation. Proper conductor sizing is crucial for ensuring both safety and performance of the electrical system. Understanding conductor ampacity involves determining the maximum current a conductor can safely carry without exceeding its temperature rating. The NEC provides tables that list the ampacity of various conductors based on their size, insulation type, and installation conditions. These tables take into account factors such as ambient temperature, number of conductors in a raceway, and conductor termination temperature ratings. It is important to select conductors with an ampacity that is sufficient for the load they will be carrying, taking into account any derating factors that may apply. Derating factors are adjustments to the conductor ampacity to account for conditions that can reduce its ability to dissipate heat. Common derating factors include ambient temperature correction and adjustment for the number of conductors in a raceway. For example, if conductors are installed in a high-temperature environment, their ampacity must be derated to account for the increased heat. Similarly, if multiple conductors are installed in a raceway, their ampacity must be derated to account for the increased heat generated by the conductors. Proper application of derating factors is essential for ensuring that conductors are not overloaded and that the electrical system operates safely. Overcurrent protection is the use of devices such as circuit breakers and fuses to protect electrical circuits from overloads and short circuits. These devices are designed to interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. Circuit breakers are resettable devices that trip when an overcurrent condition is detected, while fuses are one-time devices that must be replaced after they have blown. The selection of overcurrent protection devices must be carefully coordinated with the conductor ampacity and the equipment being protected. The overcurrent protection device should have a rating that is equal to or less than the conductor ampacity, but not so low that it causes nuisance tripping. Short circuit current rating, also known as SCCR, is the maximum fault current that a component or assembly can safely withstand without failure. It is important to select components with an SCCR that is sufficient for the available fault current at the point of installation. The available fault current is the amount of current that would flow in a short circuit condition, and it depends on factors such as the utility transformer size, impedance of the conductors, and the presence of other equipment in the electrical system. Components with an insufficient SCCR can fail catastrophically in the event of a short circuit, posing a safety hazard and potentially causing extensive damage. Understanding the 80% rule, continuous load calculations, voltage drop, conductor ampacity, derating factors, overcurrent protection, and short circuit current rating is essential for designing and installing safe and reliable electrical systems. These concepts are fundamental to the NEC and must be properly applied to ensure the safety of people and property. Ignoring these requirements can lead to dangerous situations, including electrical fires, equipment damage, and even injury or death. By following the guidelines outlined in the NEC and seeking the advice of qualified electrical professionals, one can ensure that the electrical system is installed and maintained in a safe and compliant manner. Remember that electrical work should only be performed by qualified individuals who are familiar with the NEC and local codes. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect oneself and others from harm. Always de-energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. If one is not comfortable working with electricity, it is best to hire a qualified electrician to perform the work. Furthermore, it's not just about adhering to the minimum requirements, but also about building a robust and reliable system. Considering future expansion and potential increases in load is a prudent approach. It is wise to design the electrical system with some extra capacity to accommodate future needs. This can avoid the need for costly upgrades later on. Planning ahead can save time and money in the long run. Also consider the impact of harmonics in the electrical system. Harmonics are distortions of the voltage and current waveforms that can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause a number of problems, including overheating of transformers and conductors, malfunctioning of sensitive equipment, and increased energy losses. Mitigating harmonics may require the use of harmonic filters or other specialized equipment. A power quality study can help identify and address harmonic issues in an electrical system. Proper grounding is another critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to quickly trip and clear the fault. A properly grounded electrical system can reduce the risk of electric shock and prevent damage to equipment. The NEC specifies requirements for grounding electrodes, grounding conductors, and bonding of metallic enclosures. It is important to follow these requirements carefully to ensure that the electrical system is properly grounded. Regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. Electrical systems should be inspected periodically by qualified professionals to identify any potential problems. Maintenance tasks such as tightening connections, cleaning equipment, and testing overcurrent protection devices should be performed on a regular basis. A well-maintained electrical system is less likely to experience failures or safety hazards. In conclusion, electrical safety is a complex and multifaceted topic that requires a thorough understanding of the NEC and other applicable codes and standards. By following the guidelines outlined in this discussion and seeking the advice of qualified electrical professionals, one can ensure that the electrical system is installed, operated, and maintained in a safe and compliant manner. Remember that electrical work should only be performed by qualified individuals who are familiar with the NEC and local codes. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect oneself and others from harm. The 80% rule, the 125% continuous load rule, voltage drop considerations, conductor ampacity, derating factors, overcurrent protection, short-circuit current rating, harmonics, grounding, and regular maintenance are all important aspects of electrical safety. By paying attention to these details, one can create a safe and reliable electrical system that will provide years of trouble-free service. Remember to consult the latest edition of the NEC and local codes for the most up-to-date requirements. Electrical codes and standards are constantly evolving to reflect new technologies and best practices. Staying informed about the latest changes is essential for ensuring that the electrical system is compliant and safe.